Hello students, so in this lecture, continuing our uh, series on lectures on fitting, so we will do fitting of an exponential curve. Now, exponential curve can be written as y is equal to a e to the power minus bx. So that this curve needs to be fitted to a set of x and y values. And so we will use a transformation relation. We will say that let z be equal to log of y. So if that is the case, then it will be log of e to the power minus bx. So that will make it equal to the power. So that will be an a here. Sorry. A e to the power minus bx. So it will be equal to log a plus minus bx. And we can write this equation now as equal to z is equal to e0 plus e1 x, where e0 is equal to log of e and e1 is equal to minus b. So what we have obtained, we obtained a linear relation, and since we obtained a linear relation, so we'll use the linear fitting formula that we have used. Y is equal to a0 plus a1x. This is the equation. Then what the formula that we used to find out the coefficients a0 and a1, the same thing we will use here, assuming this equation. So the normal relationships or normal equations in case of a linear fit are na0 plus summation x into a1 is equal to summation y if we put z here, so it will be z minus summation log of yi. And the next equation will be summation of x into a0 plus summation x square into a1 is equal to summation x z. This is actually z is equal to log of y, so this is equal to log of y, and summation xz, which is equal to summation of x into log y. So the solution as can be obtained from Gauss elimination method. Or you may not use Gauss elimination, you can use the normal arithmetic method, and you get the following solutions. You get A0 as equal to summation of z into summation x square minus summation x into summation x z divided by n into summation x square minus summation x whole square, and for A1 you get the denominator remains the same, summation x square minus summation x whole square, and the numerator changes, it is now n into summation x y minus summation x into summation y. So we will replace the summation z, actually this is z, we replace the summation z by summation log y, and similarly it will be replaced by summation log y and summation x into summation log y. That is how you get. And from A0 and A1 we can obtain the value of A and B. So as we have say that A0 is log A and A1 is minus B. So once we obtain A0 and A1, we can say that A is equal to e to the power A0 and B is equal to minus A1. So ultimately we have been able to find this relation A e to the power minus Bx. This is how you can fit an exponential curve. Now, similar to this, you can also have an hyperbola. So the second part is fitting hyperbola. And hyperbola is given as y is equal to 1 divided by a plus bx. This is our hyperbola equation. Now here the transformation will be z is equal to 1 by y. So we put it, and simply you can see that z is equal to a plus bx. So we have again obtained the linear form. So basic idea is to obtain a linear form so that finding out the coefficients become easier. So again we will use the linear regression relationship, that is to find out the A0 and A1, and then we will use them to find out the value, the polynomial equation of the hyperbola. The third one is if there is a trigonometric function fitting trigonometric function. This is the case. We assume that the equation is given as y is equal to a sine omega x plus phi. This is the equation. So there are three parameters here. One is your a, one is your a, one is your omega, one is your phi. So we will assume that this is a known quantity and a and phi are unknown. So we could expand it. So we can write y as equal to a sine omega x cos phi plus cos omega x sin phi, and then let me write this once again. A is equal to y is equal to a sine omega x cos phi plus cos omega x sin phi. So this is equal to a sine, let's say you can write this one as a cos phi sine omega x plus a sin phi cos omega x. Now here we will assume that this a cos omega x, let's call it as a1, and this a sin omega x, call it as a2. So ultimately the equation changes to y is equal to a1 sin omega x plus a2 cos omega x. Now using the idea of minimizing the sum of squares of the errors, so minimizing the sum of squares of error, that we mean summation of y minus y corresponding to, that is, this is the original set of values, that is the original or the given set of values which needs to be fitted, and this one is the one which is the deviation. So we can write it as a1 sine omega x minus a2 cos omega x So again we need to write the linear relationships. So this is again in the linear form. We can write the linear relationship and we ultimately get the following values. We get the value of a as equal to root over a1 square plus a2 square, and phi is equal to a tan inverse a2 by a1. So these are the two values we obtain. So hence we can find this polynomial, the trigonometric relation, not the polynomial. The exact form can be obtained. Okay. So the next fitting problem is associated with fitting a geometric function, a geometric equation. Now suppose there is a curve given as y is equal to a x to the power b plus c, and this b is a non-integer. So as in the previous case, we need to find out a transformation uh, which will do the linearization. So we assume that if out of there are three parameters a, b and c, out of this we will assume that c is a known quantity, as we have done for the case of a omega, and x in the previous case is known. So if c is known, we can write we can take c here, so we can write y minus c is equal to a x to the power b, and then we'll use the transformation equation z as equal to log of y minus c. Z is equal to log of y minus c and is equal to log of ax to the power b, so that is equal to log a plus b log x. So we have done a successful linearizing. So this is again equal, this is we take as a0, and this so we write this one as z is equal to a0 plus a1t, where a0 is equal to log of a and a1 is equal to b and t is equal to log x. So the normal equations, as we know, for the case of linear regression, the normal equations are n into a0 plus summation x into a1 is equal to summation y and summation x into a0 plus summation x square into a1 is equal to summation xy. These are the normal equation, and the solutions are as follows: a0 is equal to summation denominator will be n into x square minus summation x whole square. Write this one once again. a0 is equal to n into x square minus summation x whole square, and the denominator will be summation y into summation x square minus summation x into summation xy sorry, this is y. And a1 will be equal to the denominator will remain the same, summation x squared minus summation x whole square divided by n into summation xy minus summation x into summation y. So if we put the normal equations as for the geometric case, so we get the normal equations as equal to n into log of a plus summation log x into b is equal to summation log y minus c. This is the first equation, and the second normal equation is summation log of x into log of a plus summation log of x whole square into b, and it is equal to summation of log x to log y minus c. And these are the solutions. That's how you can actually find out the value of a0 and a1, and by finding out these values you can find out the values of log a, b, and then you can easily put them into the final geometric equation y is equal to ax by c, and that's how you get the geometric equation that you need to fit to the given x and y values.